Hi everyone, I'm just going to show two implication proofs. Okay, so our first one, let A and B be sets and consider P as the statement X is an element in A intersect B and Q as the statement X is in A. We want to prove that P implies Q, or if P, then Q. Okay, so I'm going to start by writing proof. Okay. And then I assume P is true. So you may be thinking, whoa, Danica, in past videos you have said specifically to not assume things to be true. And you're right. So you don't want to assume what you're trying to prove. But here, recall back from our past videos with the truth tables and things, if P is false, then this statement is vacuously true. So that's just a fancy word. All I mean is when P is false, doesn't matter if Q is false or true, the statement is true. Okay? So if P was false, then we'd already be done. Check. So let's assume that P is true because that's where the interesting stuff happens. So if P is true, we need to show that Q is also true, or else our statement is then false. Okay? So we assume P is true. Then X is in A intersect B. By definition, this means X is in A and X is in B. Okay? Therefore, since X is in A, Q is true. Therefore, P implies Q. Okay, you always want to write a concluding statement. Okay. All right, so that was pretty fast. Excellent. On to our second example. Let A, B, and C be sets. Consider the statements P. So P is the statement that A is a subset of B. Q is the statement that B is a strict subset of C. And R is the statement that A is a strict subset of C. So what I'm asking for us to prove is that P and Q implies R. Okay? So what I mean by this is that the statement P and Q implies the statement R. Okay? All right. So similarly to above, I'm going to assume that the if part of my statement is true. Because if it's false, then it doesn't matter if R is true or false. Okay? Our statement is true just because. But you might be looking at this and you're thinking to yourself, man, these are a lot of letters, a lot of writing. So why don't we write it like this? So another way to write this is, if A is a subset of B and B is a strict subset of C, then A is a strict subset of C. Okay? And this also might help illuminate why we assume that the if part is true. Because if the if part is false, then what are we really saying? We're not really saying anything. And that's another reason why you always want to write proof, is in case you write anything above, you don't want the reader to think that that's part of your proof. Okay? All right, assume P and Q true. Then, by definition, and so what I mean by definition is like the definition of subset or strict subset. For all X in A, X is also in B. Also by definition, for all, let's say, Y in B, Y is in C, and there exists an S in C such that S is not in B. Okay, so those are my two definitions. And so remember, you don't have to word things exactly like I do. The skeletons need to look similar, but are the same, but the meat can look different, okay? The verbiage that you used or the line breaks, it just needs to be readable for the reader. You never want to make it hard for the reader to give you points. Okay. So, well, what am I trying to show? What do I want? Let's talk about that. Well, I want that A is a strict subset of C. So I want, for all elements, let's call them A and A, that A is also in C. And that there exists some, I don't know, R in C, such that R is not in A. Okay, all right. So that seems doable from what we have here. And if you don't want to write what you want, if you kind of already have an idea of where you're going, that's completely okay. If you didn't have an idea of where you're going, that's okay too. We're still in the beginning of the course. Okay. So what am I going to do next? Well, I'm going to use the definitions that I had above. Since for all x in A, x is in B, and for all y in B, y is in C, then for all x in A, x is in C. Okay, so I hope that you followed that. So all I'm saying is, because any element that I find in A can also be found in B, oh, but any element I find in B can also be found in C. So if I follow this, all my elements in A are in B, but all my elements in B are in C, so then all my elements in A are in C. Okay? And you can also, if you're doing your homework or something, you could write this in words. If these symbols are confusing or you're worried you're going to look back on it and not really understand, I really encourage you to try to dabble with these symbols, because it will make your life a whole lot easier later down the road. Okay. Therefore, A is a subset of C. Okay, we have not shown that it's a strict subset yet, but we have shown that it's a subset. Now I need an element in C that is not in A. Okay, so let's go back to our definition up here. So we were able to find an element, at least one, in C that's not in B. Okay. So let's use that to our advantage. Since there exists an element S, let's say, in C, such that S is not in B, and how do I want to word this? Oh, okay. Okay, here's how I want to say this. Okay, sometimes you want to reword things a little bit. Okay, let's say it this way. We know there exists an element S in C such that S is not in B. Since this element is not in B, then it cannot be in A, since every element in A is also in B. Therefore, there exists an S in C such that S is not in A. Therefore, A is a strict subset of C, meaning R is true. Therefore, I know I've used therefore a lot. I'm not always the best writer, but I get the point across. Therefore, P and Q implies R. Okay, so one clarification that I do want to make is that I'm not saying that R is always true, because you could certainly pick sets A, B, and C where R is not true. Okay? But what I am saying is that if P and Q are both true, then R must be true. Okay? So in order for R to be false, P and Q need to be false. So one of them at least needs to be false. Okay? All right, excellent.